There's one that is a cooled antenna. It's very much like Herschel, we just launched, except it's got the antenna cooled. It's called Spica, and we're almost certainly going to be participating in that in a small way. A group at Lethbridge is leading that. There's a much larger antenna project. This is basically a US project, Sapphire. We'll probably get involved, but we probably won't launch until 2035, so I'm not working on that one. Because I promise I'll be retired by 2035. I'm working on a variety of interferometers, and I'll show you some of them. In particular, I'll show you Spirit is an interesting interferometer. I've been working with Esprit, which is a European one. This is a NASA project. And so those are sort of where I think the future is likely to be. Here's Spica. This is the one we're about to launch. Again, 3.5 meters. It's going to be 5 degrees. Okay, our current one is about 80 degrees. So this is really difficult to make it the whole mirror here really cold. You have to figure out how to cool all this. There's all kinds of interesting things about this. This one's, it's led by a Japanese group with partners in Europe, and we're part of the European collaboration. The European collaboration is already funded, even though the Japanese haven't formally agreed to fund their building. They're building almost all this, except the mirror and some of the other instruments. A really big, here's a current version. This is the 5th version I've seen of this 10-meter wide telescope. So this is the 10-meter telescope. This is the telescope, and this is communications with the Earth. I've seen so many different versions of this, so there's no real reason to believe that it's going to look like this in the end. But you might recognize this solar shield. This is just the James Webb Space Telescope that's under construction now for optical wavelengths, a very similar technology. Not surprising, because NASA would like to reuse the technology they're inventing for the James Webb Space Telescope. But where I really am interested in working is with interferometers because of the resolution, the ability to see fine detail. If you want to see small areas in space, you need to use an interferometer. So we have a current existing telescope called the Very Large Array in New Mexico. That's where Jodie Foster was in movie Contact when she first discovered extraterrestrial life. You can't do it the way she did in the movie, sitting out in the car. I spent an entire summer living in an unair-conditioned trailer when I was a graduate student. That's where they used to put the students. Anyway, ALMA has fantastic resolution. Going down is better. Going down here is better. ALMA is being built now. Here's its resolution. The Very Large Telescope is a telescope in, it's an optical near-infrared telescope the Europeans have built, and it will work as an interferometer. There's this gap in here, which, let's see if I have an animation. Yeah, there's the gap. The far infrared gap. There's no, at this place where all the formation processes are the brightest, there's no high-resolution instrument, and you have to go into space. And so I'm really pushing these days to build an interferometer to work at these wavelengths. So here's one version of an interferometer. It's got 3 antennas, three mirrors, and radiation is brought to the center and beam combined there and put into some set of instruments here. And these 3 satellites are held together with a tether, which can change its length, and the whole thing is rotating, so a little bit of centrifugal force. Because in order to do interferometry, you have to control, or at least, very least, know that all the path lengths between all the instruments down to an accuracy of about 1/10 of a wavelength. So if you're trying to work at, say, 40 microns, you need to know all the distances to 4 microns at all times, which is quite difficult. The size of this is, this is 100 meters or something like that. So you have to keep control over incredibly fine detail. Here's an early version of a telescope called Spirit. The current version is, this looks again like the James Webb Space Telescope, which is sun shield back here. This is an early version. I put it up because it's got numbers, but it's got a more recent version, and here's the more recent version. It's got a nice fancy NASA picture here, and it's actually down to 2 antennas, 36 meters apart, 1 meter antenna, and a beam combiner in the middle, so the signal comes down here, and a mirror reflects it into here, and this thing inside has all the instruments in it. And it's deployed on this big long boom here that's 36 meters. And so it's pretty hard to launch something that big into space. You would think this is going to be like, the space station. We're going to go up there and build this enormous long thing. And by the way, you need to have this thing spinning, and you want these antennas to be able to deploy along here so you can get various what's called baselines, the distance between these 2 things. And so that's a bit of a challenge. But it turns out the NASA engineers came up with an idea which other NASA engineers have told me is totally impractical. But I thought I'd show you on the movie. How do you get something like this into space without building it in space like that? So here it is. It's launched like that. Right? So you launch it and unfold it.
Epic music.
I added the music, they didn't put music, so I just took something. That's Agent Orange, I think is the song. So you can make something that deploys in space and does all the things you want to do. So the last mission I thought I'd mention to you is Spree. This isn't quite, I got a better picture, I got a video of the concept for this. This is another one that's put out with prime investigators for this here in the Netherlands, so they've got another SRON video to show you. This is pictures of Odin in space, supposedly with 6 of them. That was the original idea, was they built 6 things similar to Odin. There's a bunch of technical stuff that you don't really need to know about. These are free-flying antennas, just out there. They're robots, essentially. Again, you have to know the distance between them, accurate to about 4 microns or so, all the time, while they're flying up to a kilometer apart. And that turns out the toughest part of this mission is actually the robotic controls. Doing formation flying on multiple things that are, especially these are a few meters. And the hardest part of the formation flying actually is keeping them from hitting each other. And so it's a fascinating problem, but it's also nice for the artists. Here's my last slide. I didn't have the music. So the entire design is what can we fit into our current launch vehicle? So the same thing was true for Herschel actually. You have to figure out how many of these can we fit. I wanted 7 because then we can only fit 6. It's really, really good technical reasons for having at least 7. They said we can't fit more than 6. So that's the current mission design. I've been fighting this for about 4 or 5 years, telling them 7 makes so much more sense for all these reasons. Let's get a longer rocket. They said we don't have a longer rocket in the horizon, but I need a bigger rocket. Just a slightly bigger rocket. 3.5 meter diameter, because that's the biggest diameter you can put. It's the diameter of the inside of the fairing for the rocket.
Is there no way to launch them in 2 groups?
Yeah, well, I also suggested that we should launch them. I said we should probably launch more than 7. We should try to make them a little thicker to get more capability and launch maybe 2 launches. And I said I suggested more launches actually. But they didn't like that too because the launch is really expensive. Mm-hmm. So this is them all figuring out where each other is. They have to keep constant connections this is basically laser metrology, so you know where each of the satellites is relative to the other ones. But you also have to keep track of timing things. They all have to use the same radio tuner. The thing that I built for Herschel, the local oscillator, you have to have a single local oscillator that they all share. So one of them is producing, this is just saying the timing differences. Somewhere in here, one of them is going to start producing a local oscillator signal and send it up. There's the clock guy. He's sending out a local oscillator signal to the other satellites. He's sending back saying, okay, I'm coordinating with you. We can now start correlating data between these two. And so the time it takes tells you something about where the thing is in the sky. And then you correlate on each baseline. So here's the mixed signal, like the mixer signals down in the local oscillator. You do that for all 4 antennae. And at this point, you've got good, complete information that you can now record for a number of hours. And then eventually, when you've collected enough data, you send it back down to the ground station, which will be the end of the video, more or less. I've forgotten now what all the colors are. Red's the laser metrology. Yeah, so I think yellow was the clock signal and blue is the correlate data. It's the data for correlate. And then you send the correlated data down to the ground.
You said altitude?